Hello, my name is Sazhenkov, and today I will present the experimental study of AlMg6 alloy mechanical and ballistic characteristics at different temperatures and loading speeds. So 12 standard specimens and 4 rectangular plates of aluminum alloy was used as the object of study. On this slide you can see geometrical and mass characteristics for both types of specimens. The first 12 specimens was used to obtain primary mechanical characteristics of the alloy for different temperatures and strain rates. Rectangular plates was used to evaluate ballistic limit of the material and to obtain dynamic displacement and strain fields. So on the first stage of the study, quasi-static loading with 0.016 and 0.16 strain rates for 25, 75 and 150 Celsius was performed. We obtained sigma epsilon diagrams, which allows us to evaluate Young's modulus for each type of loading condition and to obtain stress and strain values at maximum load. As you can see, when the temperature rises from 25 Celsius, it's blue points, to when it rises from 25 to 75, so the stresses and strains at the maximum loads are slightly increases. But when the temperature goes to 150, the maximum stresses decreases by 10% and 26% for 0.16 and 0.016 seconds in the minus first degree strain rate. As for strains, at maximum load, there also decreases by 8%, so this point and this point, and by 32% for this point and this point. This is for 0.16 and 0.016 strain rates respectively. So the ballistic experiments was performed on the special test rig, which contains pneumatic gun assembled of the compressor, receiver, fast valve, and the barrel, and the ballistic chronograph to measure the muzzle velocity of the projectile, and 2 high-speed photon cameras to capture the impact event from elevated front and plan view. The control of the experiment was performed via PC through PXI module of National Instrument System. The specimens were aligned with the barrel as it's shown on the picture and clamped from the one side, from the one end. The presented test rig allows accelerate projectiles up to speed of 40 or 500 meters per second. It's possible to use spherical, cylindrical and flat projectiles made of the different materials with that test rig. So in our case we use the solid steel spherical projectile with the 25 millimeters caliber and 54 grams mass. So the ballistic rig also have second configuration when both cameras are located behind the target specimen to perform digital image correlation method. In this table you can see a full breakdown of the test parameters. The negative values of the resultant velocity refer to a projectile which rebounded off the target specimen after the impact. The main interest was in the assessing the ballistic limit and the amount of the energy that the sample is able to absorb. As you can see, the estimated value of the ballistic limit is about 171 meters per second. On the next slide we can see the time dependencies of the displacements. in the direction perpendicular to the target's plane for 3 different points on the target's axis of the symmetry, the vertical axis of the symmetry, the point P0 on the rear surface of the sample at the point of the collision, P2 it is near the peripheral section, and P1 is near the embedment. This data was obtained for the projectile collision speed of 71 meters per second. So there were also dynamic strain fields obtained for this case in X and Y directions. As you can see, in the point of the collision, the point P0, there is the residual strain about 3.5% for both directions, and there are also some high frequency oscillations near this value. So the strain to time dependencies obtained for these 3 points can be used to tune the numerical model of the collision process. So in the conclusion, I want to say that elastic and strength characteristics were obtained for AlMg6 material in the temperature range of 25 to 150 Celsius for 0.016 and 0.16 strain rates. So the ballistic limit of the AlMg material determined in the first approximation upon collision with a solid spherical projectile with a mass of half of the no, it's not a half of a kilogram, is 0.054 kilograms, so it's 54 grams. So the ballistic limit is 171 meters per second. So we have the time dependencies of the displacement on the rear surface of the target, the also time dependencies of the strains. And all of these data can be used to adjust the numerical models of the ballistic interaction of the AlMg6 target with the spherical steel projectile. Thank you for your attention.